This program segment covers three analog and digital concepts that are used as basic building blocks in any sophisticated telecommunications network. These three building blocks are modulation, analog to digital conversion, and multiplexing. Let's take a look at the first building block, modulation. Many technological changes have come about thanks to the principle of modulation. Modulation allows radio and television stations to share the same airspace. Modulation techniques, together with multiplexing, allows multiple voice and data signals to share a common transmission path on a wire, a glass fiber, or between microwave towers. Let's take a look at the process of modulating signals for voice and data transmission. Modulation first became widely used with the advent of the AM radio. AM stands for amplitude modulation and is one of the modulation techniques that we'll be looking at. To look at these modulated signals, we've set up an oscilloscope. It'll show us what happens during modulation. Modulated signals usually exist at frequencies between millions and billions of hertz. The oscilloscope lets us freeze small segments of time so we can display these signals. Modulation uses a carrier signal to transmit the information signal. Because carrier signals are very high-frequency signals, they make radio transmission practical. Receiving radio transmissions at voice frequencies would require an antenna many miles long, but the high-frequency carrier signals are received by antennas a few feet long. Let's take a look at how radio transmission works. A microphone creates an electrical signal from the announcer's voice. This electrical signal is called the information signal. A carrier signal is then modified using the information signal. This is the modulation step. Then the modulated carrier signal is transmitted through the air using electromagnetic waves. An antenna receives the electromagnetic waves and sends the electrical carrier to a demodulator. A demodulator recreates the information signal from the carrier signal. Then the information signal is amplified and converted back into sound by a speaker. Let's see what a carrier signal looks like. This is an unmodulated carrier signal. It's a very high frequency signal. The signal has a fixed amplitude and fixed frequency. When the carrier signal becomes modulated, we're able to track its deviation from this constant. Here we see the carrier signal on the top and the information signal on the bottom. Notice the difference in frequency between them. The carrier signal we're using is 10,000 hertz, and the information signal is 1,000 hertz. Once the carrier is modulated by the information signal, we see that changes in the carrier take place. What we're looking at is amplitude modulation. The amplitude of the carrier signal is varied according to the amplitude of the information signal. As amplitude of the information signal increases, the amplitude of the carrier increases. And as the amplitude of the information signal decreases, the amplitude of the carrier signal also decreases. This modulated carrier is what is transmitted to an AM radio. Notice that the frequency of this carrier remains unchanged. Only the amplitude is varying. Now let's take a look at frequency modulation. This is the technique used in FM radio transmission. An FM radio tuned to a station at 100 on the dial is tuned to a 100 million hertz carrier signal. On the oscilloscope, we see the amplitude is not changing. Instead, the frequency of the carrier signal varies according to the amplitude of the information signal. As amplitude of the information signal increases, the frequency of the carrier increases. And as the amplitude of the information signal decreases, the frequency of the carrier signal also decreases. Frequency modulation is better able to capture the information signal than amplitude modulation. Frequency modulation is also less susceptible to noise and interference than amplitude modulation. Here we see a carrier signal that is amplitude modulated by a digital information signal. This technique is called amplitude shift keying. This technique changes the amplitude of the carrier to represent the digital on and off states of the information signal. Amplitude shift keying allows computers to communicate using analog telephone lines. A device called a modem modulates the signal. Another technique modems use to transmit digital information over analog telephone lines is frequency shift keying. This technique changes the frequency of the carrier to represent the digital on and off states of the information signal. Frequency shift keying is commonly used by modems that transmit information at speeds from 300 to 1,200 bits per second. A modulation technique not used with analog information signals but commonly used with digital information signals is called phase shift keying. This technique instantaneously changes the phase of the carrier signal. A number of phase modulation techniques are used with modems. Modems use phase modulation to transmit at speeds greater than 1,200 bits per second. That's a brief look at modulation. These modulation techniques have made many other technological advances possible. The next time you turn on a television or radio, think of the modulating principles that make the devices possible. Now let's take a look at the second building block used in telecommunications, analog to digital conversion. When we transmit signals over great distances, they're subject to noise interference. This noise is more easily removed from digital signals, so a method was developed that digitally encodes analog signals, transmits digital signals, and reconstructs the analog signals from the digital code. The reconstructed analog signal is not a perfect reproduction, but it is very nearly like the original signal. Analog to digital conversion is a four-step process. First, the signal is filtered. It requires more digital information to encode unnecessary higher frequencies, so the analog signal is filtered to eliminate its high and low frequencies. This leaves the portion of the signal that exists between 200 and 3,500 hertz. The second step, called sampling, measures the amplitude of the analog signal at specific time intervals. Sampling produces a stream of positive and negative voltage levels at fixed time intervals. In telecommunications, 8,000 samples per second are taken. The third step, called quantizing, rounds off each voltage level to one of a number of predetermined amplitude levels. In telecommunications, 127 positive and 127 negative levels are used. The fourth step, called encoding, converts the decimal amplitude levels into binary codes. 8 bits are used to store each amplitude level. This 8-bit code is often called Pulse Code Modulation Code, or PCM code. Analog to digital conversion now is complete, and this PCM code is transmitted through the network. After the digital signals are transmitted, digital to analog conversion is performed to reconstruct analog signals. Digital to analog conversion is a three-step process. The first step is called decoding. It takes the 8-bit PCM code and converts it into positive and negative voltage levels. The second step, called reconstructing, takes the 8,000 voltage levels per second and reconstructs the original analog waveform using an electronic process that basically connects the dots. The third and final step is called filtering. High-frequency noise is created in the decoding process. This noise is removed by filtering high frequencies. In telecommunications, the frequencies above 4,000 hertz are the ones removed by filtering. This device is called a codec. It's a coder-decoder that performs analog to digital and digital to analog conversion. Some telephone sets, such as the ISDN voice data terminals, include these in the base of the set. The trend is to digitize analog signals right in the telephone and convert them back to analog at the receiving telephone. Let's move along and look at the third building block used in telecommunications called multiplexing. Only one signal can be transmitted over a given medium, whether it be a wire, microwave radio, or fiber optics. Multiplexing is a technique used to combine many signals into one composite signal. The composite, or carrier signal, is transmitted. Then demultiplexing separates the composite into the many original signals. Different techniques are used to multiplex based upon whether the signals to be multiplexed are analog or digital. Frequency division multiplexing is used to multiplex analog signals. Frequency division multiplexing takes multiple voice frequency analog signals with a bandwidth of 200 to 3,300 hertz and assigns each a portion of the composite signal bandwidth. Each portion of bandwidth is called a channel. To frequency division multiplex, The frequency of each input signal is boosted to fit into one of the channels. The signals share the same transmission path as the composite signal. After transmission, the demultiplexer uses a filtering process to separate each channel. Then the demultiplexer returns each channel to voice frequencies to restore the signal to their original form. Digital signals are multiplexed using a technique called time division multiplexing. Time division multiplexing divides time into a number of channels instead of dividing frequency into a number of channels. Instead of assigning each input channel a frequency range in the composite signal, time division multiplexing assigns each input channel a time slot. Each time slot usually contains 8 bits. 8 bits of the first input channel are placed in time slot number 1 of the composite signal. Then 8 bits of the next input channel are placed in the next time slot. After 8 bits of the last input channel are placed in the last time slot, the next time slot, number 1, receives the next 8 bits from the first input channel. The composite digital signal must be of sufficient bandwidth to accommodate all of the inputs. The bandwidth of a digital signal is measured in bits per second. If 5 input channels each have a bandwidth of 5,000 bits per second, then the composite signal must have a bandwidth of 25,000 bits per second to accommodate the 5 inputs. Demultiplexing separates the time slots into individual channels. This recreates the original digital signals. Now please return to your computer so you can learn more about modulation principles, analog to digital conversion, and multiplexing.